Hello, this is Dr. Strickland. In this video, we will conclude our investigation of the impact of one substituent on the next one regarding orientation. Take a minute to read through this one little student learning objective. These are the things you should be able to do by the end of this video so that you're ready for the more difficult things we will do together in class. All right, so I brought out a moderately deactivating group so that we could look at why it is that we think that this product produces, this reaction produces this one product, and it has the incoming substituent going to the meta position. So we're going to look at the ortho option, the meta option, and the para option, and these designate where the new substituent, in this case, the nitro group, is going to go. So either to one of the two ortho positions, one of the two meta positions, or to the one para position. And we're going to look at the different resonance contributors that are involved and see what we can see about how they compare. So in each case, we're going to have 3 resonance contributors. And remember that with resonance contributors, atoms never move. So however they are in the first one is where all the atoms are going to stay in every other one. So in the first one, we're going to put the new substituent ortho to the first one. In the second, we're going to put it meta. In the third, we're going to put it para. So they're all going to look like this. And so in order to make our first resonance contributor of the rhenium ion, I got to use the pi bond that involves the carbon where I want to put the substituent. So that would be this one. Whoop. And we need our electrophile. So we'll put it right there. So this pair of electrons is the nucleophile. This little NO2 plus guy is the electrophile. And so these 2 pi bonds stay exactly where they were. The nitro group goes ortho to the methyl ketone, and the incomplete octet, which is represented by a carbon that has a positive charge, is right there. So we're going to have 2 others. And so I'd like you to set those 2 up. So pause the video and set up those 2 and come on back. All right, welcome back. So I'm going to set up mine. And while I'm setting up mine, if you want, you can go ahead and move the electrons around. Atoms stay the same. Everybody's in exactly the same location. The only thing that moves is the electrons. So the atoms will be the same there. They'll be the same here. If atoms move, then what you have is constitutional isomers. And that is not what we're doing here. All right, so let's see. We move this pair of pi electrons down one place, then pi bond goes here, and the positive charge goes there, and this one stays where it was. We move this one over one position. And I'm going to pull this over a little bit so you can see the edge of the paper better. Here, and this one stays where it was. And it turns out, if you look at this third one, that it is particularly unstable. Because remember, a carbonyl carbon has a partial positive charge. And, you know, like charges, either 2 positives or 2 negatives, do not like to be near each other. So to have them on adjacent carbons makes this a super unstable situation. Super unstable resonance contributor. All right, let's see how the other 2 go, and then we'll come back and compare here. All right, so with the meta, we're going to have 3 resonance contributors. 1, 2, 3. I think I kind of sort of squinched myself over there, so let's do like that. Now we've got the nitro group going to the meta position. Here's our methyl ketone. Got single hydrogens on every other atom of the ring. All right, and so in order to put the new incoming substituent here, we have to use this pair of pi electrons because it's associated with that carbon. We need our electrophile. All right, like that. Positive charge on the nitrogen. The nitrogen is the electrophilic atom of the electrophile, the one that most needs electrons. So the incomplete octet is right there, and these two pi bonds are the same. All right, so I'm going to draw the other two resonance contributors, and I want you to do them at the same time. And we'll see if you can finish before I do. So atoms in all the same places. I'm going to do that first. And then we'll move the electrons around and see how it compares with that ortho option that we started with. All right, ready? Here we go. That pi bond moves one place. So the other carbon that was involved in this double bond is the one that gets the positive charge. And this pi bond stays where it was. And then this one goes here. This pi bond moves over one position. Positive charge goes here. This one stays where it was. All right, and you can see that in this case, the positive charge never goes to the atom that's adjacent to that partially positive carbon. It goes there, goes there, goes there. You know, in the resonance hybrid, when you draw the resonance hybrid for this rhenium ion, the partial positives will be on these 3 carbons and not on any of the others, including this one. Okay, so we don't have a super unstable resonance contributor here. Now you can probably guess what's going to happen here, but we're going to draw them anyway. All right, 1, 2, 3. All of them with a methyl ketone right here. That's kind of the reference position for us. And in this option, the nitro group is going to the para position. So that's over here. All right, and all of the other carbons have hydrogens. All right. So let's make sure everybody's caught up to this point. So I want you to find the pair of electrons in the benzene ring that acts as the nucleophile. Draw the arrows to form this first resonance contributor, and then draw the electron movement to get to all 3 resonance contributors, and then come on back. All right, welcome back. So, I have to use this pi bond like that. So if we want the nitro group to go here, the positive charge has to go there. And these guys stay where they are. Same kind of electron movement. We're just doing a detailed set of resonance contributors And so, you know, this kind of analysis does take time, which is why we're doing it here. But there are a lot of things where you have to go slowly and methodically through all the details to get from one end of an argument or one end of a problem to another. And so it's important to know how to do that. But when you look at these, we've got one that has one of these super unstable situations right here. You know, these guys do have an incomplete octet. These three all have an incomplete octet. These have an incomplete octet. Actually, this one has an incomplete octet too. It's just extra bad. I'll push this under here for you. So in the ortho option and in the para option, what you have is a super unstable situation, which means that the meta doesn't have anything great about it, but it's better than the other two. So for that reason, we think the methyl ketone will be a meta director because the ortho and para rhenium ions are destabilized. We know that, you know, that the meta disubstituted compound is the product, and we think this is why it happens. All right, so that is the basic story on why meta directors are meta directors. If you have any questions, please send them to me.